This screencast is on drawing line angle drawings of the chair conformation of cyclohexane. So it's important in organic chemistry class to become confident at drawing the chair conformations of cyclohexane. But it can be a lot of work. And so today we're going to go over just how to do that. The chair conformations are really comprised of three sets of parallel lines. So the first set of parallel lines is a little bit off from horizontal. So these first two lines are not horizontal. In fact, they're slanted down and they're a little offset. This one and this one starts off to the right of the first line and it's a little bit offset. Then there are two more parallel lines. So here is a set of parallel lines that you draw next. And then here's the third and final set of parallel lines right here and here for the chair. The flip has three sets of parallel lines too. Here's the first set of parallel lines down and to the right. Then here would be a second set of parallel lines. And there would be the third pair of parallel lines. Next, I like to work on the axial hydrogens. Now, I like to start at either the head or the foot of the chair. At the foot of the chair, the axial at the foot of the chair keeps headed straight down. So if this is the foot of the chair pointed down, the axial is going to keep pointing straight down. So there is an axial hydrogen in red. And then it's going to alternate. If I just went down, the next hydrogen is going to go up. And then we're going to go down. And I'm going around the ring like this. And then at the next carbon, the hydrogen is going to go up axial, down axial, up axial. And I can do the same thing on the chair flip. If I go to the chair flip and I start at the foot of the chair, the axial hydrogen goes straight down from the foot, axial down, go to the next carbon in the ring, each axial up. Go to the next carbon, each axial down. At the foot of the chair, where it's pointed upward, the axial hydrogen goes up, down, move to that last carbon here, up. And so the red are going to be axial in this drawing. And I'll switch to, let's do blue for equatorial. Now, equatorial is definitely a little bit trickier. Equatorial hydrogens are not drawn completely horizontal. They're drawn just a little bit above or below a horizontal. That's because this angle needs to be 109.5. If you drew it exactly horizontal here, the angle would be 90 degrees. So you need to get that angle just a little bit greater than 90 degrees. And so here, the hydrogen is a little bit above an imaginary horizontal line through this carbon. If I have an imaginary horizontal line through the next carbon, this hydrogen is a little bit below it. And so these are going to go up and down relative to this imaginary horizontal line. Same thing here. One is down, the next one is up. These two are the trickiest to get. The next one is down. They're just a little bit trickier to get into their places, those last two. One way that I remember how to draw them is there is something called W coupling. And so what you'll notice when you're drawing that last hydrogen is that you need to be making a W here. Or it's an upside down W, or an M, if you will, on this side. So when you're making that last hydrogen, make sure that you're making it look like an M or a W. Let's look at our equatorial hydrogens here. If our axial was up, our equatorial here is going to be down. And then we're going to alternate down, up. Here, I want it to be looking like my down, my W from here on over to here. So it was down, up, and down. And then we had up, down, up to finish off this W. So what does that coupled W look like again? Or those W hydrogens? They look like this. It helps you get the angle right. And we know that they are coupled from proton and NMR. So these two chair conformations are equivalent chair conformations. So we can represent it with that arrow that's the same size in both directions. And then the blue is our equatorial hydrogens. So let's try drawing these on our own to see how we do with drawing our chair conformations on our own. So we wanted two offset parallel lines. They need to be the same length, but they start offset from each other. Then we have two more parallel lines. And then here's our last two parallel lines. Now our chair flip needs to look like a mirror image. We'll have these two parallel lines. We'll have two more. Last two parallel lines. Now we want all of our axial hydrogens to go straight up and down. We can start at the foot of the chair, going down, up, down, up, down. Same thing over here. Start at the foot, down, up, down, up, down, up. Then we'll go ahead with our equatorials. Now, since this first hydrogen was up, the equatorial needs to be a little bit down relative to this imaginary horizontal. Relative to this imaginary horizontal, the next hydrogen's a little bit up, down, up, down, up, down, up. Over here, up, down, up, down. Oh, I missed an axial here. So let's not forget that and put in that last axial. You should see 3 axial up and 3 axial down in both drawings, and then our 6 equatorial hydrogens. And these are going to be equivalently favored or of equal stability. Let's keep putting our drawing practice to work and try trans 1,4-dimethyl cyclohexane. So we'll draw the backbone of our chair conformation. And we can go ahead and draw in all our hydrogens. We can do axial up, down, up, down, up, down. Equatorial, this equatorial is going to be down, up, down, up, down, up. And then we'll draw the opposite conformation. And we'll have axial up, down, up, down, up, down. We can do our equatorials, down, up, down, up, down, up. Now we need to replace some of these hydrogens with methyl groups, 2 of them on each to be precise, the 1 and the 4, and we want it to be trans. So let's just start right here. If we do a methyl group, at the 1 carbon, straight up. Let's check for the 4 carbon. If this is carbon 1, we've got carbon 2, 3, 4. Now they need to be trans so that if this group is up versus the equatorial, this methyl group needs to be down versus that equatorial line drawn through that carbon. So we'll replace that hydrogen down with a methyl group down so that they're trans. Now, on the chair flip, we know that any group at this foot of the chair, for example, that was down, needs to be at the head of the chair and be out equatorial. It was axial before. Now it needs to be equatorial at the head of the chair. And this old head of the chair became the foot of the chair, and it was axial before it became equatorial now. And these equatorial groups are going to be much more favored because they have much more room for that big methyl group. Here we've got a lot of strain, a lot of steric strain caused by those methyl groups and their neighboring hydrogens. So this is going to have a lot of steric strain, and having the 2 groups axial on the right is really going to be the favored conformation. What about cis 1,4-dimethyl cyclohexane? We're just getting our practice with our drawings here. So let's draw our 2 chair conformations. Now we wouldn't have to draw in all of our hydrogens. They're going to be presumed to be there if we don't draw them all in. So as we start to get more confident on our ability to draw our basic chair conformation, we wouldn't have to do that. We could go to the 1, and again, we could just make this axial up at the 1. But then when we go to carbon 1, 2, 3, 4, if it's cis, this methyl group should also be up. Well, the axial is going to be down. Maybe we could put in that hydrogen to see that axial down is not going to help us. We need these to both be up. So we're going to need up equatorial to be our methyl. This would be cis now because both methyl groups are up relative to that imaginary line that's horizontal there through that carbon atom. So 2 groups up, meaning this is both cis. We go to flip this, and the foot of the chair is going to become the head of the chair. It's going to go from equatorial to axial for the methyl. Now the hydrogen is out equatorial, and the old head of the chair becomes the foot of the chair. That methyl that was axial becomes equatorial, and the hydrogen is now axial. And so what we have here is 1 group that's axial methyl, 1 equatorial methyl. When we flip it, 1 equatorial methyl, 1 axial methyl. We've got 1 of each, and these 2 conformations are going to be of equivalent stability. And we'll draw an equal arrow between the 2 of them. Now, our last example says to draw the alternative chair conformations of a tri-substituted cyclohexane, where the methyl groups are all up, up, up relative to each other. And these are at the 1 and the 2 and the 4 carbon, at 1, 2, skip 3, and at 4. So we need methyl groups in those 4 places. It says to draw the alternative chair conformations, as in draw them both. Okay, well, they're all up. So let's start with a carbon 1, methyl group up, a carbon 2, methyl group up. Relative to this imaginary line, we need up, up. We'll skip carbon 3, we'll go to carbon 4, up. Okay, when we flip it, what we should notice right now is we've got an axial, equatorial, equatorial. We know everything is going to flip. This equatorial at the foot is going to come to the head of the chair and be a methyl axial. When we skip that, that was our 3-carbon. Right in here, our equatorial is going to become our axial up. And right in here at the foot of the chair, well, that used to be the head of the chair. It used to be axial. Now that's an equatorial methyl. And so on flipping, we get equatorial, axial, axial. Well, we're going to prefer where we're able to have 2 groups equatorial versus only 1. And so we would have a larger arrow showing a preference stability-wise for the conformation on the left. So I hope that you are now more confident in your ability to draw the chair conformations of cyclohexane.